Hello and welcome! In this episode we will finally have a moving fluid simulation. As you can see, this is the end result we will have at the end of today's episode. So then let's jump right into Visual Studio and see how we can implement that. Alright, in the last episode we ended up having our neighbor search implemented fully. And now let's see how we can do an actual fluid simulation right there. So let's jump back to Visual Studio and let's add our code for the fluid simulation. And the first thing I'm gonna do is I'm gonna implement or I'm gonna change how the gravity and the boundary condition is implemented now. This, I think we didn't implement the gravity thing till now, right? And yeah, now we're gonna do that first, so we can see our particles flowing, well, not flowing, but falling to the bottom. So let's do that first. Let's implement the method apply gravity. And I'm gonna disable my GitHub Copilot again. There we go. Gravity. And in here I have a for loop. I'm just going to copy this one. And here I'm going to say this dot particles. And oops, I want to have the velocity of the particles. So velocity is equal to add. And I'm going to say this dot velocity. I'm just going to copy this one too. Paste it in here. And here I'm just saying scale it's the gravity with the delta time. Gravity with the delta time. All right. Yeah, and the gravity will be a acceleration, not a force, so that's fine. And I don't need to call this dot apply gravity. I want to say this dot gravity. Okay. And of course I need to set the gravity to, and I'm gonna set the gravity to let's say new vector with a gravity of 1, just 1. There we go. All right, and then we can apply our gravity too, and we are doing this at the first call here in our update method. So this dot apply gravity, and now when we jump back to the browser, it should actually well have a gravity there. And I have to add the delta time here too, and here of course the delta time too. All right, so let's jump to the browser and refresh. Oh yeah, and you can see our particles are now falling down, and they are slowly accelerating too. Cool. And here you can see now our boundary, which just inverts the velocity. So they are going to the top again, and they're now like a wave, I guess. Okay, so now we will change the volt boundary. And in this one, we will just set the positions. We are not flipping the velocity anymore. We will set the position of a particle and the previous position of a particle to the boundaries. So let's add the previous position here too. I'm going to call this breath pos. and I'm gonna copy this line here and say ref position. Okay, and then if this position is smaller than 0, then I'm saying particle dot position dot x is equal to 0, and I'm saying the same thing for the previous position. Oops. Come on. Right, and the previous position 0, 2. Okay, and then we need to do the same thing for the y. So, all right, and then for the x again, and here I'm gonna say actually I think we don't need these variables. Well, actually, yes, we don't need the previous position here. Here I'm gonna say canvas dot width, and here too, and I'm just gonna say -1. All right, and the same thing for y2. Okay, and now of course we need to change the width to the height. All right, and now I think we have everything for our boundary. So let's jump to the browser and refresh again. And now the particles should just stick to the floor. They shouldn't bounce back. So let's wait for that. Come on. Okay, yeah, that looks good. Cool. So, and now we will change the update method a little bit. And in the update method, we apply the gravity. Then after this one, I want to predict the position. So I'm going to move the neighbor search out after this dot position predict position, and I'm also going to remove the mouse position now. And between the neighbor search, actually, 1 second. Yeah, I want to change the world boundary to, and I'm going to place it right there. Actually, I think it doesn't matter really where you're going to put the world boundary, if you put it to the compute next velocity or right there. I think it might be better to leave it after the compute next velocity. So I'm just gonna redo my thing here. And between the neighbor search and this compute next velocity, we will implement the double density relaxation. So the main algorithm to simulate our fluid motion. But before that, I think I need to change the simulation because we removed the mouse position right there. And I'm gonna remove this one, the mouse position here. And also in the neighbor search method, I want to remove everything except these two method calls. Okay. Good. And then we can implement the main algorithm. I think I'm going to do it like right there. And this method will be called, you guessed it, double density relaxation. 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 Did I write that right? Yes. All right, and this method will have a delta time. And I'm gonna call this right there. So this dot double density relaxation with the delta time. All right. So let's implement this one. All right, but before that, we need to add some new constants to our simulation. I'm gonna move this one just a little bit down there. And here I'm gonna say I'm gonna declare the constants we need, and this is 1, the rest density, and I think rest then density, there we go. And this will be, I'm just saying some numbers I think which are good. Maybe you need to find out some good values which will work for you. I did that a couple of times, so I know approximately what's good for the simulation, with which values might work. And the rest density here is just a value which says if a particle if the surrounding of a particle will have a density of lower, or which, yeah, when the density around the particle is going to have a lower density than the rest density, then there will be an attraction force, and if it's more than the rest density, there will be a repulsion force, basically. And if it's the same, then the particle is like in its rest state. Then we have a k near variable, and this and this is a constant for our near density calculation. There are 2 densities we're gonna do or calculate. Then we have a normal k. For our normal calculation of the density, I'm gonna set it to 0.014. Actually, I'm gonna say 0.02. And then we have the interaction radius. I'm gonna set this one as a constant too. And this will be 25. And I'm gonna pass this interaction radius to the fluid hash grid. All right. I think these are all we need. Let's create our double density method. In here, I'm going to iterate through every particle. So I'm just going to copy this for loop. And here I'm going to calculate the pressure, the density. In the first for loop, we have multiple for loops. The first one, well, actually, there's just one whole for loop, and in this for loop, there are 2 separate for loops. And in every of these for loops, we will get the density and then the pressure. The first step for us is to calculate the density. So let's start with this one. So the density, I'm going to initially set it to 0. And then we have a density near. I'm going to set this one to 0, 2. And then I'm going to retrieve all my neighbors, all my neighbor particles. So this dot fluid hash grid, get a neighbor of particle index, and this will be current index of our for loop. And then I'm getting the current particle. I'm going to name it particle A. And this will be this dot particles at our current index. Right, and then we have another for loop, and I think I'm gonna copy this one too. And this will be a for loop for our neighbor particles. So I'm going to change the ice to 1, to y. Yeah. And then I'm just saying neighbors.length. And I'm going to iterate through all the neighbors. And here I'm going to retrieve my particle B. This is neighbors, my new index. And I'm also saying if particle A is the same with like particle B, I'm just going to continue. I think we already avoid this scenario, but it's just a backup. Then after this one, I'm gonna get the direction to my neighbor particle, or in this case also this is the gradient, and I'm gonna say particle B dot position with particle A dot position. All right. Then I'm calculating the distance, and this is my direction vector times the length. And I'm dividing it by the interaction radius, and then we have the value between 1 and 0. And if this value is smaller than 1, I will add to the density. Well, I'm going to calculate the current density from that particle. And with the formula from the paper, we have to say math.pow 1 minus calculated value here times 2, or with the power of 2. And I am going to say the same thing for the density near. But this time it will be with the power of 3. And this is our density calculation. Just gonna make sure that I have everything right, but it looks pretty good. Yeah, that looks fine. And now I'm converting this density, these two densities, to two pressures. And we can do this by using a equation of state, is it? It's called. You see this equation pretty often when you do smooth particle hydrodynamics. And yeah, this is just the density minus this dot rest density times a constant. Then you get the pressure out of it. And in this paper, there's also a pressure near. And this is calculated by just saying this dot k near times the density near. So this is smooth particle hydrodynamics, and this one is an addition from the paper. And then I have another variable called particle displacement. Displacement, better. And this is a vector 2, 0. And the particle displacement will be, actually, it must have the name particle A displacement. This will be the particle, well, the displacement for particle A from the pressure. So we're calculating the pressure, and from the pressure we will get a force, and we are calculating the force to a displacement basically, and then we add this displacement to our particle A. That's why it's called particle A displacement. And here I have another for loop, and I'm gonna copy this for loop here again. Actually, I just can copy the whole for loop because it's quite similar. So let's paste it in, and I'm gonna remove these lines here. And I'm gonna change this letter to a P. Oh no, sorry. I don't want to change this to a P, I just let it be. And that is fine. This looks fine. Yep, that's all good. All right, yeah. Then we have the if again. I'm gonna check again if this one is smaller than 1.0. And now I'm gonna normalize our gradient or our direction. And then I can calculate a displacement. And here we are calculating now the normal value. And then we can scale this value with our normalized vector, and then we have a displacement vector, and then we can add this displacement to our particles, and that's it for this algorithm. So we are converting the pressure to a displacement now, and this displacement term, I'm going to call it displacement term, is calculated by using, again, a power with the delta time, power of 2. And then, and then we have to calculate the pressure times 1 minus Q times math.pow with 1 minus Q times 2. Okay. And of course I made a mistake here. This one is not a multiply. We have to do that with a plus sign. And here I'm multiplying the math power function with the pressure near. And now that's the right one. So I'm just gonna place this one in the next line. And there you go. I think this is everything for the displacement term. Delta time by 2 times the pressure 1 minus Q plus the pressure near times the math power. All right. This is everything. And now we can use our normalized vector and scale it by the displacement. So let's do that. And in the paper, this is called D for displacement. And I'm going to call it the same. And we can just say scale our gradient or our direction vector with the displacement term. Now we have our D, and now we can say particle B dot position is equal to add, and we take the particle B position again and say scale again. We just take half of the displacement and we're going to apply the other half to our particle A. And that's it, basically, what we need to do. But I need to do that in a other way for particle A. And I'm going to say here the particle displacement A with scale of D and 0.5. And then I'm saying after the for loop, I'm going to apply this displacement there. All right. And I think that's everything. So let's apply the displacement to particle A, and this is just particle A dot position. Then we're adding our particle displacement. And here we need to use the particle A position with the particle displacement. All right, and that's everything we need. I'm gonna check for errors, and I'll be right back. Okay, so the first error I found is I made a small typo. This needs to be called scale. Okay, and then we need to change some values. First, I'm gonna pass a static data time. So in the playground.js file, I'm gonna pass here data time with 0.25. And I also need to change some parameters, because if you go to the web browser now and refresh, you will see there is actually something happening, but it's still not right, and that's because our parameters are not good enough to do something. So let's go back to the simulation and see what we can do to change that behavior. I changed my values k to 0. I think I'm just saying 0.015 and k near to 0.1. Rest density is 40. I think that's fine. If I go now to the browser and refresh, right, it's still not enough. I'm gonna take a look and I'll be right back. All right, I think I figured the perfect parameters for our simulation now out. And if we go to, again, the simulation.js file, I'm going to change the rest density. Well, no, I'm let it the 10, the rest density, but I'm going to change the k near to a value of 3 and the k value to 0.15. Then the action radius will be the same. And that's it, yeah. Just if you have a different result, then just try which values are best for you. I'm gonna show you what will change when we change the simulation parameters. What I also gonna change is the offset between particles. I wanted to set it to 10 now. And also, I think I made a small mistake. We actually need to place the world boundary condition between the double density and the compute next velocity. All right, and if we now go back to the browser, save and refresh, and there we go, we have our little fluid now, and yeah, it's flowing around. If I change the particle size now to, for example, 2000, then yeah, we will see it's gonna work. And now let's see what's happening when I change some variables. I'm gonna change the k near now to 4. Don't need to change it, just want you to show what's gonna happen. As you can see, the pressure will increase and the particles are having a higher repulsion force. Let's see what's happening when I change it to 6. Yeah, it's gonna be more and more. Let's see, I'm gonna change it back to 4. And I'm gonna change now, well, actually, I think it was 2, right? Was it 2? No, it was 3. And I'm gonna change now the k parameter to, let's say, 2. Refresh. And maybe you already saw it. Let's change it to 0.4. yeah, the pressure now goes in the opposite. The K value, the less the K value, the higher the particles will um, get attracted to each other. And if I change this to 0.6, yeah, it's going to be a higher value. Well, a higher attraction force. Let's see what's happening when I change K to 1. I guess it's just going to be a blob. Yeah, kind of. All right, yeah, that looks really, really cool. All right. Yeah, I'm gonna change it back to 0.5, for example. Let's see. Cool. All right, that's everything for this episode. Thank you very much for watching, and see you in the next one. In the next one, we will probably add viscosity to our simulation. But yeah. Yeah, see you in the next one. Have a nice day, and bye bye.